First of all, you can go to this QR code and join our community. There are a lot of ideas there, a lot of discussions. Please raise your hand, those who joined the community already. Yes, more than at the beginning of the conference. Well, the subject is how we struggled with one exponent. I am Georgi Alexandria. I'm a magician of the 6th level and also analyze source code, static analysis of source code. Application Inspector is developed in Positive Technologies. Application Inspector analyzes source code and finds potential dangerous vulnerability. It helps us to find it quickly and eliminate them faster. In our team, we have a few vacancies. If you are interested, please go there and leave your data. So what are we going to talk about? This is what we're going to talk about. I wanted to joke, but this is true. How true or false is the slide? We're going to find out. So, first, in this presentation, we presume that we have a one-thread program without parallelism, without quantum applications, without quantum calculations. We describe one algorithm and not several ones. So I understand, I believe that you understand that. We're going to talk about abstract interpretation and symbol execution. And these are the links. We believe that abstract interpretation is interpretation of the code without its actual execution. For example, we want to find all the rules, all the management routes. And for example, if all the arguments, injection points, requests to the file system, requests to databases are all unknown. So, this is the example of the symbol execution. We have an injection input argument. This is a local variability. It may have one value or the other. If it matches the condition, it's one thing. If it doesn't match it, it's the other thing. Now, to talk the same language, let us describe two terms. First, variant. Variant is a pair, x and y, where x is a certain value and y is the condition of reachability of that value. If x is a Boolean value, so x is the implication in its pure form. We shall use the following expression. We shall consider two options as equal when both components are equal and the values are equal. Then variative array. Let's look at the simple. So is the argument local variable and certain values different branches, and in line 8 we have a variative result. So potential vulnerability operation is meant here. The vulnerabilities that we try to reach. So we believe that they are right here. For example, let's take the following number of parameters. We have variable x and y. X has certain values and y has certain values. And in the end, we shall make a request, and we have two options in x and also two options in y. What are we going to get? Concatenation gives us four options: x1, y1, x1, y2, x2, y1, x2, y2. If we had more variables and more options, so the number of results would grow exponentially. And we would like to realize how fast it will grow and what we can do about it. Then, after that, we shall have pure mathematics. Let's find out. Cortege is so a Descartes. Well, each IT projection is a certain element from that multitude. Well, I think this is not very clear. Let's look at the exponent in Descartes. It's encircled, enclosed cycles. For example, each call has a certain value of I, J, and K. So the number of elements in Descartes aggregate is then equal to the compute value 5 by 5 by 5, 125. Exponential function. The number of calls of compute will grow up exponentially. We shall have a very, very high number. Descartes gives us the following results. Now, let's see the set, the n sets. And for example, we have a G function, a function of the programming language. Concatenation of n arguments, conjunction of n, call of functions, and so on and so forth. It doesn't matter. Now, let us see the promote. It takes the sequence, the condition of all the sequences, and then adds all that in G function. And out of these two functions, it builds an option. P, as you can see, P is variative set for G with x1 to xn. And promote shows us that the number of elements here is equal to elements in Descartes product. In the symbol execution, we have an exponential number of elements that we have to look at. What can we do with the exponent? It's too much. We can do nothing. We have a working algorithm. It works. It may take hours, months, years to look at each and every element. We want everything fast. That's why we would like to accelerate all that, because exponential chart is it's a fundamental problem of the analysis algorithm, and you cannot solve it quickly. Full stop. But as we could say, improbability is not a constant. So it's a fundamental problem. But can we work out something? For example, we have a huge number of elements, exponential number. Some of them have false conditions. Let us enter the R function that will discard the elements with improbable results. The number of elements after it will not be larger than before the R function. So if we attach R to promote, so it will be a bit, the number of results will be a bit smaller, but how smaller, we don't know. We're going to skip promote and put it this way, R x1 by xn. Let us presume that we have variative sets and conditions, and it so happens that some of them, and maybe all of them, are equal. It so happened, for example, the input parameters, local x, and in line 8 we use x plus x, the variative set of x, and the second set of the same value. We call it a coincidence, and then we don't have an exponent, we have a linear dependence. Instead of exponential growth, we get linear growth. It's too bold, and we cannot do it. We have to prove it. Let's try to prove it formally. Looking back at our initial example, we have the input argument, the same function, x concatenated with x. The local variable is x, x small, x big, and the program which is executed at this point of time, we can have only one value in x, no more, no less. From the viewpoint of symbol execution, it says us that the local variable must have only one value at a certain condition. At a certain, not always, but at a certain condition. If we take in our variative set x, small x, fix a certain option, say that we have a specific fixed value, in all the options that we use, we shall have this value. At a certain time, we can change it, redefine it. Then the previous one will be not valuable, because at this time that value is valuable only, all the rest is non-relevant. So by fixing this, we're going to use only this option only. All other options are not reachable. They are false. So we get only one option if we use this fixed value. We fixed it, it's 1. It was more than 1. The number of values should not exceed n. Then we try to implement it, and we were shocked. We reduced the number of scanning by more than 1.5 times, by actually 1.7 times. We were shocked like this. Can we do anything else? Let us think. In the previous example, we didn't use the two options which are equal. For example, we have a set of conditions and they are not equal. let us presume that the conditions are the same. For example, let's look this. There's a small function and two local variable, x and y. And we combine them in pairs. And in the end, we do the concatenation. We have different values, but conditions are the same. x1, y2, x1, y1, and so on. We believe it's conditional. We believe that, sorry, to begin with, variative sets have one serious condition. We call it a theorem of options. If we have different conditions, any two options which are not equal have contradicting conditions. For example, we have options 1, 2, 3, 4, 5. If we take any pair of them, the result will be false. If the power of our set, the number of options in, it's okay. If we have only one, it's okay, no problem. If we have two options, for example, the first local variable is unconditional. X is equal to 5, for instance. No problem. For example, we make the second value under condition A. All previous values become false, but they are false only under condition A. If A doesn't happen, then and then only all the previous values become true. So, in that case, all the previous values should have a condition, no A. If no A, then true. For example, we have k number of elements, and all of them have contradicting conditions. For example, let's describe k plus 1. All under condition A, it's true. All the previous ones under condition A are false. So we get a new variative set. The previous are true without A, the last is true with A. So the last element with A is false when without A. Let's come back to what I said before. If we have common conditions, the number of elements is not exponential, it doesn't exceed k. It's a serious condition that we have to prove. In the theorem of options, we have fact 1. All of them are false except condition A. Now let's take one set of condition, fix one point ym in the I power, xm in the I power. We shall see that that value will be present in all conditions. In fact 1, we say that no matter which value we take, it will be false. Fact 2 says that ym, for example, is present in the first and up to the last set. whatever set we take and whatever option we take, it will be false in promote. Always except one case, when in the first, in the second, and in the last case we have condition A. We have only one possible true option. And we can fix k number of conditions. So the number of options doesn't exceed k. Okay, we proved it. Then we try to enter it in the application inspector. We accelerated scanning by more than 2 times, by 2.2 times. We were shocked. We had a question. What else can we do to optimize it even better, to reduce the time? Now let's have a look. Let us presume that our sets are not equal, the conditions are not equal. But let us presume that the condition has some common points. The number of options in all sets coincides. It looks like that. We have a number of arguments and 2 local variables. The first has 2 values, the second has 2. And then again we add more and more values, and in the end we concatenate them. And in X we have 4 options, and in Y 3 options. 2 of them have one common condition. From X we have 2 options which coincide to Y options. We call it a scoop. Well, this is not convenient. The number of options here wouldn't exceed the sum of the elements and the product of differences between those options. We're not going to prove it. Well, but let us say that if we have an element in this area, it will be present in all the options. Then there are 2 cases independent of each other, and we shall merge them later. For example, let's take one variative set, fix a certain option, and say that this condition exists here. Let's regard all promotes, all the positions. Since we have these options, in the cross-section it will be present in all variative sets, whatever we take. We believe that whatever set we take, they will be false. Out of these 2 conditions, we say that we always have false cases except one case, when in each set we take an option with our condition. We can have k number of such options. Let's look at the right part of the equation. When our condition, fixed condition, is not in the cross-section. Of course, we take an option, promote all the cases. Since the element is not in the cross-section, we know that all the rest will be false. Whatever case we take, it will be false with our condition. Since we have a cross-section, we shall have all this element in all the sets. What do we get as a result? We'll get false in all cases when, with our fixed condition, we take the element in all other variative sets of this cross section. We can have true values only when in all other conditions we'll take elements which are not in this cross section. We can have the number of elements here minus this number of elements, and we have to multiply them. Initially, we said we have one element in the variative set, and we can have more than one. And we get k multiplied by what I just described. After this proof, we tried to use it in the application inspector, and we get more acceleration. We accelerated the scanner by 2.5 times. Instead of 10 hours, we get 4 hours. You know what is 2.5 times. So we already got used to it and said, is it enough or shall we do something else? Due to certain reasons, I'm not going to show you anything else, but I can tell you just that some other steps are possible. Let's go back to our chart. There is one interesting thing. In Application Inspector, we couldn't use all the cases that we have. So actually, the results might be even better. But at this point, I am going to finalize my presentation. I am too fast. I am Georgi Alexandria. I am a leading developer. We are looking for more people. We have vacancies. If you are interested in algorithm optimization, if you try to work with context-dependent grammar, what if you try to use extended formulas, non-filtered arguments in forgery, please come to us and let's go to our magic school, Application Inspector School, where you are welcome. This is not all. At the end of this track, you can evaluate my presentation by going to this link. Leave your feedback, positive or negative, and take it into account in the future conferences. That's about all, and if you have any questions, I'm ready to answer them. Questions or comments? Hello, I liked your strive for improvement. Are you using ready-made solutions or did you develop them? So we have both, our own and IZ3, SU4. We use the 5th version now. I cannot tell you about our own ones. Do you evaluate quality? Yes. Can I read about it? No. There was one question there. Thank you for your presentation. Please tell me what is the average number of analysis of the project? What kind of project? Different project, different languages. We have a set of examples. So we have about 40 projects for young. So about 40 projects for different languages. What is the statistics of for heuristic cases? The first statistics the average scanning time. I showed it to you. And second is non-heuristic, because we formally proved it. Thank you. More questions?
Good morning. Thank you for the presentation. Your open source library launches, have you been able to find any errors? Well, answer, that's beyond the topic of this presentation, but yes, we did find. Question, did you report it? Answer, we did some, we did not some others. There was one question here in the center of the tent. Thank you for the presentation. Okay, simple execution is quite a peculiar type of analysis. It seems to be used as an addition to something else to generate input data in prephasing or K-symbol execution. So what are we trying to look for with this analysis? Answer. We can find the vulnerabilities where data travels from input to output, given that all input data may not be known. There were some input arguments of integer type. So we'll be looking at the output, anything that is integer. If an input is a condition, then we'll look for a condition in the output. So this is simple execution per se. Okay, and in terms of life cycle in SD secure development, it's clear when to do static dynamics or dynamic analysis. What is this? This is static analysis. A question. So is this a stage in static analysis? Answer, yes. There are various types of analysis, but this is the one that we looked at here. There's one more question here in the room. Yes, hi, thank you for your presentation. My question is this. Throughout your presentation, you have discussed about how you came up with an assessment of the number of elements in the set, and that we can see that the number of elements would be lower. And then you said that we changed something in the analyzer to reduce the number of these elements, it seems. So even though the presentation talked about the number, but the analyzer works with the content of these elements. So can you please explain? Okay, you proved that it would be linear or linear multiplied by the product. What changes did you do in the analyzer for it to analyze quicker? Thank you. The question is clear. I won't be able to give you a detailed answer for clear reasons, but let me give you a high-level answer. Because we get a smaller number of elements, then the enumeration, the analysis of these elements takes lower time. And then it's not that we simply look at those elements. We've got to do something with them. So it means that we've got to do those actions with a smaller number of elements. Okay. I don't want to keep you here for 30 minutes. It's not my intention. If no questions, thank you very much for coming here. Wish you all the best at Positive Hacking Days.